In part A of the question, we are asked, how far does the cab move while accelerating to full speed from rest? So we have drawn two segments of this elevator cab's journey. This is the first segment right here, and we are just told that it starts from rest. So the initial velocity, of course, would equal 0 meters per second. And it's reaching, quote, full speed. And we know that the maximum speed is 305 meters per minute. So the final velocity would be 305 meters per minute. For some reason, they gave it in meters per minute. We need to convert that into meters per second. So we'll do a quick conversion here. We know that 1 minute is equal to 60 seconds. And if we multiply by that conversion, the minutes will cancel, and this will give us meters per second, which turns out to be about 5.083 meters per second. So that would be the final velocity. We also know the acceleration is this 1.22 meters per second squared. So we can write that down as part of our list of known values. Now we're looking to calculate how far the cab travels in this first segment of its journey. So we're looking essentially here for delta x. Let's take a look at a relevant kinematics equation. Here it is right here. We can go ahead and plug in the known values that we listed above. Now we can go ahead and we can eliminate this term here. This is just 0 squared, and we can square the left side as well. We end up with about 25.84. We can also multiply 2 by 1.22. This gives us 2.44 times delta x. And then finally, let's just divide both sides of this by 2.44. And when we do that, we should get a delta x of approximately 10.6 meters. So that is how far the elevator cab has traveled in that first segment of the journey. This is the correct answer to part A. Let's go back and take a look at our picture now. Now, this is a more to-scale drawing of what's going on here. Now, what we just figured out is that the cable car, or whatever it was, traveled 10.6 meters for this part of its journey, and it reached its maximum speed of 5.83 meters per second. Now, a little bit later on in its journey, it's going to have to come to rest. So over on the other side, right about here, it would still be traveling at the 5.083 meters per second, but then eventually it comes to rest. So that final velocity over here would be 0 meters per second. Now, it's still accelerating at the same rate for that final part of its journey. So that means this distance right here is also 10.6 meters. Now, what we do need is the amount of time required for this elevator car to go from rest up to the maximum speed. So we're going to take a moment here to calculate that time right now. And we can do that rather easily with the following kinematics equation. We know the final velocity equals the initial velocity plus acceleration multiplied by time. The final velocity was that maximum velocity for the first leg of its journey. The initial velocity was 0, so we can knock that out. And then the acceleration was the 1.22 meters per second squared. Now we can easily solve this for time by dividing both sides by 1.22. And when we do that, we see that the time is about 4.17 seconds. So it took 4.17 seconds for the cable car for that first leg of its journey. We can come back here and label that accordingly. It's also going to take 4.1 seconds for the cable car to come to rest because of the symmetry of the motion. Remember, it starts out at the 5.8, goes to 0 under the same acceleration, so it's going to require the same amount of time to stop. What we need to figure out is the time during this mid-segment of its journey. We don't have any of that data, but if we look carefully at the drawing, we can figure out what the delta x is for that segment of the journey. How can we do that? Because we know the total length of travel was 190 meters, and we also know that the first and last segments had 10.6 meters of length. So to get the length of the mid-segment, we would take 190, subtract off the first 10.6, as well as the last 10.6. And we end up with about 168.8 meters. Now, why did we do that? Well, we know that during that mid-segment, there's no acceleration going on. The elevator is just moving along at a constant velocity. And so we can consider the following equation. We know delta x is equal to the initial velocity times the time, plus 1/2 times acceleration times time squared. But as noted, the acceleration for that mid-segment is 0. It's just moving along at a constant speed. So this term would actually drop out here. We could then plug in that delta x that we just calculated for the mid-segment of its journey. The velocity, we know, is that constant 5.83 meters per second, and then that's going to be multiplied by time. We could divide both sides of that by the 5.083. And when we do that, we get a time of 33.2 seconds. That is how long the elevator cab is traveling for the mid-segment. So now we just need the total time. We have the time for the first segment of the journey, the time for the mid-segment, and then the time for the last segment of its journey. Let's add those together to get the total time. And when you do that, you will see that the total time is approximately 41.5 seconds. So this would be the correct answer to part B. Thanks for taking the time to watch the video. If you're interested in making a small donation to my cause, I would greatly appreciate it, but please do not feel obligated to do so. I appreciate you taking the time to watch regardless.